So I seem to have picked up a little bit of a cold, but hopefully my voice will hang in there. Can you guys hear me at the back? Yep. Great. So last time, we're all the way back to yesterday, we saw that we could write down a type system for a language that talked about security, and we sketched out most of a proof that the type system actually enforced non-interference. And then I started to talk about how to deal with non-determinism in the language and in the semantics of the language. And I want to say a little bit more about non-determinism and then and about concurrency, which is a major source of non-determinism. And then I'm going to talk about downgrading, which is a feature that we saw showing up in the GIF programs that I showed you yesterday. Okay, so last time I said if we want to express the semantics of a language with non-determinism, we're going to use small step semantics instead of the big step semantics that I used, and I said a little bit about how to prove things with such a language. But the question then is, what are we actually going to prove? And the challenge here is that in a non-deterministic language, the semantics of a command or program that we run is naturally not going to just be a final state. Right? So we were talking about things in terms of final states that we got to, and our notion of non-interference was about the final state. But if our initial configuration of the system is run in a non-deterministic language, this actually may be a set of final configurations or states, or a distribution, or maybe something more exotic, like a mixture of distributions. So what does that do to our notion of security? Right? So we need to talk about, what does it mean? If you remember, our definition of non-interference said if we have two states that are indistinguishable to the observer, then their behaviors should be indistinguishable to that observer. And what should we do to this definition? How do we define this if the thing that we're comparing is something like a set? So I claim that that's not obvious. And my evidence for that is that there have been quite a few papers written about it, disagreeing with each other. So I think the definition that I like, well, I think there are two definitions that are maybe most worth talking about. One of them is an idea called non-deducibility. So this is an idea due to Sutherland, I think 87, thereabouts. And so Sutherland's idea is, you imagine that you have the adversary running the two hypothetical, running the two hypothetical executions of the program, like we had before, our S1 and our S2, and the adversary sees a particular output from the run. So one of the elements of the set of final states or set of traces is seen on both sides, and now the adversary has to say, well, are these do these allow me to deduce that the two things are different from each other? Well, so the idea of non-deducibility is, well, if each of the observations you got from running it, so if the particular observation you got from, say, running S1 is something you could have gotten from running S2, then seeing the S1 thing doesn't tell you that you're in S1. You still could be seeing the S2 run, and vice versa. If the S2 run is something that the S1 run could have produced, then then you're not sure in some sense that you aren't seeing the other thing. Okay, so then what that's saying is that, to formalize that a little bit more, we're saying that these two sets, S1 and S2, are indistinguishable if for every possible trace that we see, or final state, whatever the things are these sets are made out of, for everything that we could have seen in S1, there exists something in S2's behavior, such that we're not able to distinguish these two traces. Okay? And there's room for tweaking exactly what our notion of the adversary power is still in this relation. And, of course, this is actually supposed to be symmetrical, so we're also going to require that for all T2 and S2, there exists a T1 and S1, where these things are still indistinguishable. Okay? So that seems appealing. And now I'm going to tell you why it's broken. Okay, so it's appealing because it sounds intuitive, and you can also enforce it with the same type system. So the same type system I showed you, if we add some kind of non-deterministic choice to the language, for example, we could add a non-deterministic choice C1 box C2. The idea is that this is going to either run C1 or run C2, and it non-deterministically chooses which. So that would be one way of adding non-determinism. We could just type check that with the same kinds of rules that we saw yesterday, and we'll be able to enforce this non-deducibility, and that might be good enough. Actually, for integrity, non-deducibility might be good enough for a lot of settings. But for confidentiality, I would argue it's not. Okay, so suppose we have the following program. So what it's going to do is assign a secret variable into a public variable. Or, non-deterministically, it might choose to assign into the public variable a random value from 1 to 100. Okay? And let's just suppose that the secret is a number from 1 to 100. Right? So, is this program secure? What do we think? So, that assignment from secret into public looks awfully fishy, right? Yeah, Anna?
Wouldn't it depend what a secret could be? Is it a value between 1 and 100?
Yeah. Let's suppose that this is contained in 1 to 100. Yep. Yeah.
But execution, if the pub is secret, if you execute it a lot of times, pub is secret will be executed more.
Right. Yeah, exactly. So, imagine, so here's the argument that it's secure for some definition of secure. What are the possible behaviors that we can get out here? Well, we can, at the end, we could end up with pub being assigned the value 1 and the value 2, and so on, all the way up to 100, right? And it doesn't matter what the value of secret is. All of these things are possible results of running the program. So this is going to satisfy non-deducibility. From any one run, we can't tell whether secret had any particular value. Okay, but on the other hand, obviously, if you ran this program a whole bunch of times, and you saw a series of outputs like this, 17, 42, 11, 42, 42, 77, 40, right? You kind of know what secret was, right? So that's a sense in which non-deducibility is not really satisfactory. Okay, and notice that this is even true even if the adversary doesn't control the nondeterminism, right? If the nondeterminism here was just pure probabilistic choice, we'd still end up leaking the value of secret. If the adversary, on the other hand, can influence the nondeterminism, and often we want to have systems where that is the case, then the adversary might be able to do even worse things to us, right? The adversary might be able to steer it so that we're always running the left-hand side, right? So, for example, if you think about this program, we'll say pub is set to secret, and then in parallel, we'll set pub to rand 100. So now the nondeterminism lies in how these different executions are interleaved with each other, the assignments to pub. And the adversary may well be able to influence which one of these things happens to run first. So, for example, on a real machine, the program is sometimes taking cache misses. And if the adversary knows that the code on the left-hand side happens to conflict in the cache with some piece of memory that the adversary is able to do things with, then the adversary can push this out of cache and cause this right-hand side to get an advantage in running. And then since this runs first, then the last thing that happens is assigning the secret. And so the adversary can steer things in the way that we want. So what that says is that if you want to use non-deducibility as a notion of lack of leakage, you're kind of implicitly assuming that you have a kind of angelic non-determinism. It's right. If this was really going to be secure, the only way to do it would be to have the random choice be balanced. Actually, I don't even think that even works in this case. There's no way to make it work, is there? Yeah, because this is going to generate an even distribution, and no matter the angelic non-determinism in this case would have to always choose the right-hand side, right? Any amount of choosing the left-hand side would tend to leak the secret, because it would make the probability distribution get a blip, right? So in general, if you want to, for non-deducibility to actually give you indistinguishable probability distributions on an output, you would need a really, really smart non-deterministic refinement solving the problem, figuring out which side of the non-determinism to execute. Yep.
So you say non-deducibility doesn't work, but you're allowing the attacker to observe a large set of runs. While in my intuition, you should allow only to observe only 2 runs and take a decision.
Mm-hmm. Why 2 runs? Oh, I see. Well, I think we should distinguish between the formalism that we're using to define what it means to be secure and the way that we would actually think about the security of a real system when deployed. So real computing systems typically get used more than once and more than twice. And so we have to think about what information people can learn. Now, if you really know that this thing is kind of a one-shot deal, and the inputs will never be used again, right? Then maybe this is good enough. But it really comes down to, I think, a more complicated argument than just the simple non-deducibility argument. So if we can look at all of this from an information theoretic standpoint and say, how much information does the adversary learn? And even then, with a one-shot execution, you have learned something, right? So if you run it once and you see 42 come out, then you have learned that 42 is more likely to be the secret than any other value. So from an information theory standpoint, and if you saw 17, you'd learn 17 was more likely too, and you'd be misled. But so you don't always learn everything, but you are learning something from seeing those runs. Okay. So, but I don't want to. I actually was not planning to talk about probabilistic things. So from my perspective, the key problem here is that this program P that I wrote down at the top is a program that has an insecure refinement. That is, we have a non-deterministic program. Our normal notion of correct, an implementation of that program is correct as long as it exhibits behaviors that are allowed by that program. And one of those allowed behaviors is to simply run the left-hand side all the time. Right? And the left-hand side is something that's clearly insecure and doesn't satisfy non-deducibility. So this is what's known as a refinement attack. So the idea is you have a system which looks secure according to non-deducibility, and non-deducibility is what's known as a possibilistic security condition. So it's a security condition that looks at the possibilities and compares them. So, and the problem is that possibilistic security is not preserved under refinement. In other words, we can reduce the set of possibilities and get out something that doesn't satisfy the security condition. So that's not great. I think it's, if you have non-determinism in your system, then you would like your security conditions to be preserved by refinement. Okay, so what's the alternative? So if we want a security condition that lets us allow some non-determinism, but is preserved under refinement, then that leads us to low security observational determinism. Which I'll abbreviate as LSOD. So this is an idea that was introduced by Roscoe in, I think, 95, and in the context of process algebras. And here the idea is that if you have any kind of adversary observable non-determinism, then it's kind of like, you can think of it as kind of an antenna that's sitting up. Non-determinism says you can go either way, and you're not really told which way it's going to go. And so something could influence it, and maybe something you don't want to have influence it. So it's sort of this, it's picking up a signal that's hard to identify. And so that's sort of inherently dangerous. So any kind of adversarial non-determinism is subject to refinement attacks. So what would it take to rule out any kind of adversarial observable non-determinism? Well, what we'll do is we'll require that from the perspective of the adversary, the system looks deterministic. So we're going to have the same kind of picture that we had with non-interference, where we have a whole bunch of states that look equivalent to each other, and we run the program, run the system, and if we started from states that are equivalent to each other, we should end up with states that are equivalent to each other. So, in other words, if we want to compare the sets sorry about that. If we want to compare the sets of outcomes from running two configurations S1 and S2, then we're just going to simply require that everything in S1 looks like everything in S2. Which sounds pretty draconian, but is something we've actually been able to use. So you might be worried that this is too restrictive. So let's talk about whether this is actually a usable notion of lack of information flow in a non-deterministic system. So here's something that might give us pause. According to this definition, if we say pub gets true, and then non-deterministically pub gets false, that's considered insecure. Because we have two different runs, which, regardless of what state we start in, could give us two different outcomes that are distinguishable by the adversary. And similarly, if we ran these things in parallel, we'd also have the same issue. I'm not actually that troubled by this. And the reason is that this is not, well, for one thing, I don't think you should really be writing code like this. So I don't feel like this is a piece of code that people are sad that they can't write. Now, it looks like this isn't leaking any secrets because there are no secret variables here at all, right? We're only assigning to public variables. But if you think about running this kind of program on a system that maybe has some secrets on it, right? There's some other secret variable somewhere, then that secret could still potentially influence which of these non-deterministic choices gets made. And so this goes back to my comment about the antenna. These programs are kind of like dangerous antennas that are maybe picking up some signal, and if the adversary can just figure out how to steer the non-deterministic choice between these two things in such a way that it's correlated with something secret, then the adversary can leak information. So that's a reason to think of this as insecure. Okay. And in a sense, that's what's happening when you look at these attacks like the meltdown and Spectre attacks that I talked about yesterday. Right? Those are cases where we're creating a correlation between some non-determinism, the time that it takes to read memory locations, and something that's secret. Yeah, question?
So, I agree about I don't want to write this kind of programs, but if I want to write just a program that just non-deterministic computations and they are low, this is in any case not considered not secure according to this definition.
That's right.
A trivial example can be the random function.
Right. So I think the right way to think about that is actually to think about it in terms of probability distributions. And I think we should then be talking about indistinguishable probability distributions rather than indistinguishable outcomes. That would be because if it's really a probabilistic choice that's being made, then the adversary doesn't have control over it, right? Assuming it's implemented correctly. So I think that's the right way to solve that problem. So we can lift all of this to talking about probability distributions, and then you still get to write your nice random choice functions, which I agree are important. Okay. Great. So another thing that we might be worried about, though, is whether we just lost our ability to write programs with concurrency. That might be more problematic. So in particular, if you imagine you write some program, and it does some command C in parallel with some command C2, then normally the semantics of execution say that we non-deterministically choose which command gets to advance at any given moment. Right? There's some kind of interleaving of the steps that are done, and the idea is that the scheduler gets to non-deterministically choose. And what this said over here was, in some sense, if you say this program is secure, what we're saying here is we're trusting the scheduler. We're saying we're trusting that the scheduler is not influenced by the wrong people in some sense, right? So this program is basically, you could say that this is what's been called scheduler-dependent security. So with the right scheduler, this is fine. But if we don't want to make assumptions about our scheduler, and generally it's kind of dangerous to make assumptions about the scheduler, then this is not going to be fine. Because the scheduler himself may be picking up secret information, may be affected by secret information. Okay. So now if we think about running some arbitrary command, as opposed to these commands over here, which are racing to update this pub variable, there may be some commands that are actually fine to run, even with any scheduler. So for example, if my program looks like x gets 1, and in parallel, y gets 2, and then I go on and do some things. So this is a kind of Forkjoin parallelism. The kind of parallelism that actually people are able to code up and it mostly works. So this kind of Forkjoin parallelism seems kind of okay, right? Because there's no program here, at least assuming there's no other program that's able to look at x and y in parallel with all of this. Neither of these two threads here is actually seeing the updates that the other one is making. Right? They're operating on disjoint parts of memory. So we'd like to be able to allow this. Right? We'd like to be able to allow this kind of harmless scheduling choices without having to make strong assumptions about what the scheduler is going to do. And the justification for making these harmless scheduling choices is that these two threads aren't really talking to each other. They're not interacting with each other. They're not interfering with each other. Okay. So let me show you an example, a more troubling example, which we have to watch out for. Let's see. So that program looked okay. We'd like to be able to type check that program and say, yep, it's all good. Here's a program we would like to stop. Suppose we say x gets true, and then if some variable h is true, then we'll do some long computation. We'll delay for 100 steps. And otherwise, we'll skip. So if h is false, we'll drop right through, and we'll set x to false. And then in parallel with all of this, we will delay for 50 steps. And we will set our low variable, our public variable, L, to the value of x. Okay? So think about what this is going to do. So if h is true, then we're going to get a long delay, which will be longer than it takes to do all of this stuff over here. And we'll set low to have the value true. If h is false, then we'll fall through to here. We'll set x to false, and then this low will assign false to L. So this whole program then is, under reasonable assumptions about how this code gets scheduled, is equivalent to just assigning h into L. Oops. Right? And you'll notice that it looks mostly pretty harmless, right? You've got, we have a variable x. We're going to claim that x is a low security variable. It's only assigned constant values. And so it looks like it should be fine to assign x into L. Right? So this is all based on timing. So this program in particular has what we call an internal timing channel. An internal timing channel is a channel where we have threads that are effectively timing each other. And the key here is that these threads are actually racing with each other. So we have a race between these two statements, right? One is trying to read a variable, and one is trying to write to that variable, and there's no synchronization that's causing them to happen in any particular order. And so they could happen in either order, and which order they happen in, of course, is leaking information. Right? Okay, so that's an internal timing channel, and effectively what it does is it allows the program to convert internally to itself. It converts a timing channel arising from these various delays into a non-timing channel, what Lamson called a storage channel. Maybe data channel would be a better name now, but that's Lamson distinguished between timing channels and storage channels. Okay, so in other words, we're making it so that the value of x is correlated with the value of h, and using timing to do so in that race. Okay, so we'd like to be able to prevent that from happening. Okay. So the question then is, how can we allow... There are two questions, as usual. One is, how do we actually enforce all of this? And then, what did we actually enforce? And naively interpreted, the definition of low security observational determinism that I gave is not going to allow even the program on the far left. Because but it all comes down to this question of, when do we actually consider traces to be indistinguishable from each other? So if we think that the trace contains all of the events that are happening in the program, then this program looks insecure, because it allows x to happen before x to be assigned before y and y to be assigned before x. If those are both low variables, then that looks like a distinction that a low security adversary could observe. And so we don't have this property that I was describing, that all of the possible behaviors need to look the same as each other. Okay? So the trick here is that we can actually play with our definition of the trace equivalence to allow that kind of harmless non-determinism. Yeah, question back there.
So in general, is our model of the adversary including that they can observe the values and variables as the program is running? Because if you just consider they can only observe it at the conclusion of the program, then that notion of like ordering the trace wouldn't matter. Like only the second kind of program would be bad if the values can change as opposed to just what it's set.
Yeah, so we could define it that way. Often when we're thinking about these systems and we want to write down a security condition, we grant the adversary more power than they deserve. And if you think about it, that's actually kind of good. Because if you're secure against a stronger adversary, and you can still write all the programs you wanted to write, that's better than if you're, or at least as good as being secure against a weaker adversary. And then by assuming that the adversary can see all of these internal events, then, well, I mean, we are actually secure against adversaries who can do that, and it actually simplifies the reasoning that we do about the thing. So, if we can prove that it's secure with respect to that adversary, then we can clearly prove that it's secure with respect to, you can only see the final element in the trace. Okay. So let's assume that the trace T is a sequence of states. So T is going to be S, S prime, S double prime, and so on. Maybe an infinite sequence. Now, the key thing that made this work was that the two threads weren't really talking to each other. They were affecting different locations. So if we assume that we can partition our state into locations that are going to be disjoint across different threads, then we can allow this kind of interleaving, harmless interleaving choices. So let's suppose that we have some set of locations. and which I'll call M. And so these will be subsets. So any given location will be a subset of the state. And we can think about the projection of a trace T onto one of those locations. Basically, picking out only we take all of the states and we just pick out the part of the state that involves that location, and we get a new trace, a kind of simplified trace that eliminates things that we don't care about. These are going to be the things that happen in the other thread, in some sense. So we could say that T sub M is going to be the state S just projected onto M, S prime projected onto M, and so on. Okay? So then we define our notion of two traces being indistinguishable from each other to a low observer as in the following way: the subtraces T1M, or maybe the projected traces T1M and T2M, are indistinguishable at the level L. So we only look at the part of the trace that involves these locations, the particular location that we're interested in. So the idea is that you're not allowed to compare updates, the timing of updates to different locations. And that will allow, by allowing this flexibility, then we can have this harmless interleaving of different reads and writes to locations happening during execution. Okay. We have to watch out here because we want to allow. These traces are going to involve events from different threads. When one thread is working, the other thread is probably not doing anything, or in many semantics it won't be doing anything. And so its part of the trace will just kind of stutter, right? You'll get the same state, S sub M, S sub M, S sub M, for a while the other thread is making progress. And so to deal with that, we also take these traces modulo stuttering. So we collapse adjacent identical states. Okay? So this is going to then allow us to have the non-determinism we want for building at least some class of interesting concurrent programs. Yeah?
Could you restate what DM exactly is?
So the M is some subset. M is some subset of the things that the state maps from. And so TM is going to be just the restriction. So S sub M is going to be the restriction of that mapping to just the things in M. And then TM is then what you get when you take each of the states and restrict it in that way. Yeah, thanks.
This way probably you are able to express determination in sense.
Great. So one more shoe needs to drop here. It has to do with the termination sensitivity. So if we want this to be termination insensitive, then we're also going to not require that the traces actually be completely identical. If we have a finite trace, then we only require that it agree with the other trace up to the common prefix. Okay? So it's going to be indistinguishable up to the common prefix. Essentially, this is like what I was saying last time, that the adversary, if the thing seems to hang, the adversary doesn't jump to any conclusions and try to learn anything from it. Now, if that bothers you, you can always stick onto the end of, assume that when a program returns, it actually generates some extra last event that says, program finished. And, yep.
Could you clarify what you mean by prefix?
Well, just there's a,
Okay.
TM is this sequence of states, right? So there's some prefix. So if you have two traces, here we have T1M and T2M. And imagine that T2M is only this long and T1M is this long. Then we'll just require that this part here is equivalent.
Okay.
Okay? So the observer seeing this one basically assumes, in the absence of seeing some final program done event, assumes, well, I'm not sure that it isn't the same as this guy because it might still just be running and hasn't gotten around to emitting more behaviors. Yeah?
And when you say for the common prefix, is that before or after you do the stuttering?
That is after you do stuttering.
At that point, couldn't you say that one thread is, or one of the two that you're comparing has gone, basically one farther than the other, is stuttering more times than the other?
Right, so if we did that, then we would be trying to address external timing channels. So we're only interested here in internal timing channels. Well, I mean, we're going to be interested in external timing channels too, right? But the distinction here is we're interested in what the program can do to convert timing channels into storage channels. And this stuttering thing doesn't help it do that, unless there's something else racing against this whole thing and timing it. So an external timing channel is a timing channel where the external timing channel is one where you have somebody outside the system measuring time. So the adversary has a clock. And the adversary is measuring time directly, as opposed to trying to make inferences about things based on the relative order of events that happen during the program execution, right? Okay, so in reality, we care about both of these things, but it's nice to have a way to enforce internal timing channels and separately from external timing channels, because external timing channels are hard. Yeah, a whole bunch of questions. Yeah, back there?
Still not super clear on how you pick M. So in the program, I pick M as equal to X and Y. I would then say, I would conclude wrongly that we have distinguishable traces when we want to say it's indistinguishable, because I want to separately evaluate M as X and M as Y.
Yeah. So that's embodying a kind of choice about the power of the adversary. So if we have X and Y in the same M, then we're kind of saying that we have an adversary who can look at both X and Y simultaneously, and then can see which order they actually got assigned in the two threads. So probably the right choice here would be to just have X and Y be separate locations, capturing the idea that we're not allowing an adversary who can see both of those things simultaneously and time them against each other. But if we want to have the ability to talk about certain locations that the adversary can time, then we can put them in the same location. I think there's more room to fiddle with this model and probably make it more precise. But yeah.
Student asked for 5 minutes break in between. Sorry.
Okay. Yeah. All right. Give me 2 more minutes, and then I'll give you a 5-minute break. How's that? Because I think we're at a pretty good break point here. Okay. So I just wanted to say. So this is sort of a nice theory, I would claim. There is a paper by Steve Zdansiewicz and myself in CSF W03, which defines a message passing concurrent calculus based on the join calculus, and that enforces this notion of security. And since then, there have been a couple of other implementations, at least, that I know about. So there's an implementation by Steve Chong and his group based on X10. X10 is a program for a language for building concurrent systems and concurrent distributed systems. And so they developed a program analysis and type system for enforcing this low security observational determinism. And there's also an implementation of this in the Joanna system by Snelting and others. So there are some implementations that actually take this approach, and I think are interesting to look at. But I think there's more to be done. Okay, why don't I give you guys a 5-minute break, and we'll continue with downgrading. Let's start talking now about downgrading, another one of these tricky issues. So far, we've been talking about systems that are trying to enforce non-interference. And the problem here is that if we require all information flow to obey this ordering, and this lattice ordering that we defined, that's pretty darn restrictive. And so when you look at real systems, as I was commenting yesterday, that you discover that non-interference isn't really the best description of what you want. So real applications need the ability to downgrade information. For example, to be able to release sensitive information under certain conditions, or perhaps to be able to take in information that is coming from an untrusted source, but then use it to compute something that is now trusted. So what that tells us is that the real security goal that we're aiming for when we build a computing system is not actually non-interference. Now, does that mean non-interference is useless? Well, no, I would say definitely not. If you're not able to enforce non-interference, if your security mechanisms can't enforce non-interference, then you really don't know what's happening, right? You have a system that could be leaking information or getting corrupted by untrustworthy information all over the place, and you have no idea where it's happening. So non-interference is still a good starting point, but we want to be able to enforce more nuanced notions of security. So there are two kinds of downgrading that we're interested in here. So downgrading is when we're moving things against the direction of secure information flow. And so when we downgrade confidentiality or secrecy, that's called declassification. So we'll have a declassify operator that does that. And downgrading integrity is called endorsement. So we'll have an endorse operator for that. Okay, that's actually a term that Steve Zdanswick and I came up with, because there was no term. So now we're actually in a world where we want to be thinking about both confidentiality and integrity at the same time. And that's going to complicate our life in various ways. So here's a kind of picture of the lattice of information flow labels. And so information is allowed to flow upward in the lattice. And now I'm going to be drawing a lattice that has both confidentiality and integrity in it. And previously I was using a diamond to just kind of represent the generality of a lattice. Now I'm not going to have enough dimensions on the board to give a full account of things. So I'll use one of these dimensions to represent integrity. Integrity increases as you go downward in the lattice. And confidentiality increases as we go upward. So now when we are declassifying information, what we're doing is we're reducing confidentiality. So that represents a movement in this lattice kind of like this. And when we're endorsing, we're moving downward by increasing integrity more than it looks like the data should be trusted naively. Okay, so the question is when do we need these things, and can we help people use them correctly? So the general problem with reasoning about downgrading, well, at least one problem, is that there's no one reason why downgrading is appropriate. So the justifications for why it's okay to do downgrading really depends on the application. And so it's hard to capture all of the different possible reasons why it's okay in any kind of simple type system. So let me give you some examples of downgrading and to give you a sense of the scope here. So imagine we're building a password checker. This is a classic example. So a password checker checks whether a secret password is equal to a guess provided by potentially an adversary. And so it tells the adversary whether the guess was correct. And in doing so, it releases a little bit of information to the adversary. Even if the adversary doesn't know the password and they guess and it says, nope, that's not the password, go away, the adversary learns, the space of possible passwords has been reduced. It just learned a little bit about the password, right? From an information theoretic standpoint, doesn't learn very much. And that's the justification. So a password checker might look like this. Something like, when we declassify whether the guess is equal to the password, and let's declassify it, and let's also specify in our declassify operator what the source and destination labels are. So we're going to take it from a high label to a low label. Then maybe we set some login flag to be true. Okay? And so the justification is based on the idea that we know that the password is actually chosen from some large space, and hopefully with a probability distribution that is such that you really aren't learning very much. So from an information theoretic standpoint, the leakage is small. Okay, so that's one possible reason why. Another possible reason why we might need downgrading is one we saw yesterday, and that is we're trying to build a game. So, for example, we could be building a distributed version of that battleship game. We have players A and B. Player A is sending moves over to player B, saying where player A wants to drop bombs on player B's board. And so these variables, mx and my, have the integrity only of player A. Right? Player A generated them. Player B doesn't trust player A. Okay? So I'm going to use a left arrow to represent integrity policies. So this is saying these are things that have the integrity of player A. And actually, up here I probably should have written H right arrow. So this is going to be a confidentiality policy. And this one here is integrity. Okay. And so then the code is going to say something like, if the move is legal, I'm going to write actually code that would be more or less legal in the GIF programming language. You get to write what are called checked endorses. So you can test some Boolean formula that can include the things that you want to endorse. And so if that's true, then we're going to endorse mx and my from A left arrow to B left arrow. And if all that's true, then we're going to apply that move to B will apply that move to B's copy of the board. Okay? So that's an example of an endorsement. So what's the justification? Well, basically, this is the way that games work. Right? It's the rules of the game that A gets to decide what their move is, as long as the move is legal. How about a third example? Suppose we want to compute the average of a set of salaries. So each of the salaries is confidential, right? So we would like to compute the average of the salaries in such a way that it doesn't leak anybody's salary. So how do we do that? Well, we'd probably write something like this. We say, take the float, compute the average, set that to be the declassification of the mean of all of the salaries. And perhaps we would also like to throw in some Laplacian noise, because if we want to use a differential privacy mechanism here. So with appropriate parameters. And we'll declassify then from a secret label to something that is public, right? And so the justification here for this particular one is differential privacy. And some analysis that really lies outside the scope of what is probably reasonable to ask the type system to do. Yeah, question back there.
Endorsement is meant to be a downgrading of integrity.
Yes.
You mean even the diamonds, but that's full integrity ever in the other direction?
No. So downgrading means the down here is with respect to information flow. So downgrading integrity means increasing the integrity. Does that make sense? So integrity is a measure of how trusted the information is. So here, let me label this. So if we think of these, of H and L, not as labels per se, but as principles in the system, then where L is kind of the least trusted principle, then L would naturally live here in the lattice. So this corresponds to something that has the least possible confidentiality and integrity. So if you think of L as like a machine that's on the network, controlled by the adversary, you don't trust it to enforce anybody's confidentiality or integrity. Whereas H would actually be over here. And then down here, at this point, we have something that's trusted by H. So this has maximum integrity and has no confidentiality. So this is like a public, trusted thing that, like Wikipedia, except better. Okay? Then up at the top here, we have information that is secret to H. Could have any secrets at all in it, but is completely untrusted. So it's sort of toxic, unusable garbage that you probably shouldn't look at. I'm not sure what the web equivalent of that is. You can think about it. Okay, so that's kind of the that I like you to have. All right, we'll pick it up if. Okay, so on the one hand, we have a lot of reasons why we would like to use downgrading. We're going to need it for pretty much any real application that we try to build. And on the other hand, the reasons why it's actually okay to do it are very application specific. So that's interesting, I think. Now, the problem is, if once you throw in downgrading, you no longer have non-interference. So what do you have? And in particular, once you have downgrading in the system, the adversary might be able to exploit it to cause damage. So let's take a look at what can happen if we have downgrading and we don't use the right reasoning in the way that we're suggesting we might be able to do. So let's think about the password checker, for example. So imagine we have a password. It's a string, let's suppose, just for simplicity. And its initial label is H because it's both trusted, right? The password had better be trusted. You don't want the adversary overwriting your password. And it's also secret. So it lies over here. That's where the password is in our lattice, right? Okay, and then we're going to write a check password routine. And it takes in a guess. And let's say that the guess is also labeled H. And then let's do the code that we had before. We'll return the declassification of whether the guess is equal to the password. Okay, and we're returning this as, I should have written down this. Let's see. So, let's suppose we're just going to return it as L. Okay? So, this looks like it should satisfy all the rules that I've told you about so far. I didn't actually give you a rule for declassify, but let's think about declassify as just kind of a typecast for now. Right? So declassify is something that takes the label and changes it to a new label. Nothing actually happens at runtime. It's just like a typecast. Right? And yeah, okay. So what's wrong with this? Well, actually, there's something subtle that an adversary might be able to do. Let's, okay, I see what's wrong here. So let's suppose that the password let's suppose that we're just in the 2-point lattice with H and L right now. Okay? So we're really just thinking about confidentiality. There's no integrity in the picture. Okay? In that case, an adversary can do something, perhaps a little bit surprising, which is the adversary can overwrite the password. With some other secret. Okay? There's nothing in this, if these labels represent confidentiality, there's nothing in this that says that the adversary can't change the value of the password. Because it's only a confidentiality label. Okay? And so then the adversary so what the adversary does is they overwrite the password with some secret that they would like to know the value of. And then they use the check password function. And they can test whether that secret has the value they're interested in. Imagine that there's some secret like, attack at dawn. Will the army attack at dawn? It's either true or false. You write either, attack at dawn or not attack at dawn into the password thing, and then you try to log in with that value. So you've now managed to leak this other secret by using the check password function. So this is an example of laundering this other secret by exploiting the fact that there's a declassify in there. If the declassify weren't there, we'd be fine. This wouldn't work. But it's exactly the fact that there's a downgrading thing sitting there that's potentially usable by the adversary for their own purposes. Yep?
So if like the string was like static final or something, so it's immutable, would that prevent something like this?
Right, so what you're asking for actually is some kind of integrity. Right? You want to be able to trust the password and trust that the adversary can, right? So far I haven't told that there's any trust in this particular example. So you've kind of identified the missing ingredient here. Which is trust. shouldn't be just sort of randomly declassifying things without some trust. And so what that's telling us is that up until now, as far as you know, integrity and confidentiality are just kind of these independent dual things that have no interaction with each other. But what we just saw is, actually, they're connected. Once we have downgrading in the picture, they actually need to have some relationship to each other in order for that downgrading to be okay. Okay, so we need sufficient integrity in order to be able to securely declassify. That's the key thing. Okay? So, and there are really two parts to this. We want to prevent the adversary from affecting what is declassified, as in the example I just gave, right? In the example I just gave, the adversary changed the value that was being declassified by overwriting the password. So that was the adversary affecting what is declassified. We also want to be able to prevent the adversary from deciding whether something is declassified. So what is declassified? This will be the label of the value that's being declassified. Whether something is declassified, that has to do with the integrity of control flow. So that's just going to be that PC label that we talked about before. We're going to be interested in the integrity of the program pointer. Okay, so now I'm ready to write down a typing rule for declassify. And this typing rule is enforcing what we call robust declassification. So, and this is from a paper by Steve Zanswick and myself in 2001. Okay, so robust declassification tries to capture this idea that you need integrity to declassify. So to keep things simple, imagine that we have a command that lets us assign to a variable the result of declassifying another variable, y, and you can declassify from some label L1 to some other label L2. Okay, we'll try to write down a typing rule for this. So, first of all, the resulting label L2 had better be able to flow into X. So, we'll require the L2, L2 needs to flow into X. And Y needs to be able to flow into L1. And now we need to make the magical jump from L1 to L2. That's the downgrading step. So we'd like to be able to say that somehow L1 is able to flow into L2, except it doesn't. But what we're going to do is capture how much we're allowed to do, how much downgrading we're allowed to do by adding some stuff to the right-hand side of this comparison. So we'll join L2 in the lattice with something that captures how much declassification we're allowed to do. And that how much we're allowed to do depends on both the label of the value L1 and the PC. So we're going to take L1 and the PC and roll them together. Now we're doing here a confidentiality comparison. But we're interested in the integrity of these two guys. So we need to somehow be able to map integrity levels to the corresponding confidentiality levels. So we're going to invent an operator that does that knows how to change things around in the lattice. Okay? So this is the notation that we use. We call this the view operator. So it's going to tell us, so what this tells us is the confidentiality level that the integrity of PC and L1 in combination are both trusted to declassify. Okay? So intuitively, what's happening with this view operator is we have our lattice. We have a label L1. We have a label. There's a label L, which is somewhere along this, and it's equal to L1 join PC. And then if we just look at the integrity projection of this label, then in some sense it's a point along, it represents this whole line through the lattice. So I said we were going to use left arrow to represent integrity projections. And what this view operator does is it reflects things around the horizontal axis and gives you a corresponding confidentiality level. Actually, we don't need to do it actually picks out the integrity projection. And what this then defines is a region where declassification is not allowed. Okay, so in this region up here, there's not enough integrity to do a declassification. All right? This is a little bit mind-bending when you see it the first or second time. So let me just say a little bit about the semantics now. So there's a typing rule. What did we get semantically? So we're talking now about systems which leak information. So before we were drawing pictures where we said, well, if you start in equivalent states, you end up in equivalent states. Well, that's not true anymore. We're actually talking about systems that by design are leaking information. And so you might start in equivalent states and end up in not equivalent states because there's a leak there. So what robust declassification is saying is, yeah, we're going to have some leaks. We're going to have some information release that's caused by using declassification. But the adversary can't increase the leakage beyond what's already there. So any violations of this equivalence that we are induced by running the program are going to already be there regardless of whether the adversary had done anything. Okay, so let me then try to make that a little bit more precise, and then we'll stop. So let's think about how to characterize what the adversary does. Right? The adversary, we said the adversary might be corrupting the password. Right? So the adversary is causing some effects on the system. So let's denote by what the adversary does the letter A. So A will be the attack by the adversary. And so the idea, you have some state S, and there's some parts of that state that the adversary is able to affect, depending on the labels on the different parts of the state. So the state say they're not really trusted. The adversary gets to stomp on them however they want. Maybe sticking in data, maybe sticking in code, because maybe it's that part of the system is actually a machine with running programs. Okay, so I'll denote by S A bracket is going to be the state S with the attack A applied to it. In other words, the adversary did their damage. Okay? Now, if the adversary gets to change anything they want, then there's a problem. Like if the adversary writes an attack that directly reads confidential data, then you've kind of already lost. So we have to limit the adversary to attacks that make sense. So A must be a fair attack in our terminology. That is, it can't directly break the non-interference properties. It can't directly steal information. It's only going to do its damage by living within the rules and causing the existing things, like the downgrading mechanism in the password checker, to run amok and release information that they weren't supposed to. Okay? So it can't violate non-interference itself. It's only in composition with the state F that it's going to do that. And we can, for example, capture that by saying that it has to type check in a low integrity PC. That will prevent it from stomping on any high integrity variables and doing other damage. Okay, so then semantically, robust classification looks something like this. We say, for all possible states S and S prime, and all possible attacks, A and A prime. Okay, so we're going to consider 2 states and 2 attacks. Then, if we apply some attack A to state S and the same attack to state S prime, let's consider the case where that attack didn't actually release any information. In that case, we would like it to be the case, and by the way, this attack A could be the null attack. Like the adversary doesn't actually do anything. They just kind of leave the state alone, the passive attacker. So what we'd like to say here is the attacker gets no benefit by attacking. So the passive attacker is just as good as any active attack, where they try to replace code and data. So if the passive attacker, intuitively, doesn't actually cause any information to leak, then any other active attacker should also not cause any information to leak. Okay, so that is semantically what we want. Okay, there's another little thing here, which is we need to restrict the set of attacks to ones that are relevant in some sense. In particular, imagine an attacker who is really stupid and causes the program to just go into an infinite loop. That would be a dumb attack, right? And maybe it would be kind of a denial of service attack. But from the standpoint of stealing information in a termination insensitive world, pretty dumb. So anything they do that doesn't send into an infinite loop will be better than that. And so we restrict the set of attacks that we care about to, in some sense, the non-stupid attacks. So no attack is better than any other non-stupid attack, is essentially what this is saying. Okay? So the thing to notice here is, how many traces are we comparing? These are actually 4 traces. So when we were talking about non-interference, we were talking about 2 traces. In fact, when we started out, when we talked about just ordinary correctness by refinement, then if you wanted to find a counterexample to correctness, counterexample was 1 trace. Right? If you want to find a counterexample to non-interference, then you needed to find a pair, non-interference, you needed to find a pair of traces that started out looking the same and ended up different. So your counterexample was then 2 traces. So what that tells you is that non-interference and actually low security observational determinism, these are what are called 2 safety properties, where the counterexample to obeying the property is a set of 2 traces. And what we're seeing now is robust classification is actually a 4 safety property. You have to come up with a set of 4 traces to demonstrate that you're not obeying it. And in some sense, what this is, so robust classification doesn't actually capture all your security requirements. You can think of it as kind of a meta requirement. Your real application security policy, the thing you really want to influence, probably is described as a 2 safety property. And what robust classification is telling you is, well, that's all great, but make sure it satisfies this 4 safety property, because if you have a 2 safety property that doesn't satisfy this 4 safety property, you probably have a problem. Okay, so I'll stop here since I'm running over. Sorry about that. Thanks.